welcome back to terminal velocity. Now, suppose there is an object falling, okay? So in the contrary to what you believe, say here's an object that's falling this way, okay? Do you accelerate forever? Until you hit the ground, that is. The answer is no, because if you do, you'll start burning. Air resistance, you remember the space shuttle re-entry, how hot it gets? And actually it failed a couple of times and it killed the entire crew and the whole thing blew up in the air, right? Meteors, those are rocks. They are, it has a pretty high combustion temperature. And they blow up in the air because it gets so hot. You know what I'm saying? So you cannot accelerate forever, so wind resistance will slow you down. Well, it's not slowing you down, but it stops acceleration at some point, okay? So let's draw the force diagram to get to the bottom of this. So one force is this. My computer is frozen. Whenever I start recording, this thing happens, right? You have this, mg meaning gravitational pull by the planet, right? Now, even this is not constant. If you go with really, really high altitude where the satellites are, gravity actually is proportional to the 1 over r, right? So it actually gets smaller. But where the airplanes fly, yeah, it's pretty much constant. It's negligible difference. So let's assume it's constant. Otherwise, this differential equation, well, it's way beyond the scope of this course. Let's just say it that way. So constant acceleration downward, the force due to gravity. Now, and then there is a wind resistance or air resistance, right? And that happens to be proportional, so some proportionality constant times velocity itself. Really? Okay, let's just look at this, right? This K is known as a drag coefficient, by the way. So it purely depending on the geometry of that shape. If it looks like a torpedo, then it has a very tiny drag coefficient, so it will accelerate quite a bit, such as a bunker busting bombs. So this will speed up quite a bit, and it can, with some hardened tip, it can penetrate the bunkers and go underground very deep and then explode underneath, okay? Or conversely, if it looks like an umbrella or parachute, then it has a huge drag coefficient, so it's going to stop that acceleration really fast so it can safely land on the ground. You see the idea? So the K depends on the geometry of the shape, okay? Now, is it really depending on the speed? Yeah, let's do a little mini experiment. If you wave your hand like this, you don't feel that much air resistance in your hand, right? I mean, you kind of feel it, but not really, right? It's not like your hand is like, unlike in water. But if you stick your hand out in a moving vehicle on freeway at that speed, then you really feel the wind in your hand. You know what I'm saying? So that air resistance, that force, resisting force, is depending on the velocity itself. So far so good? Okay, so this is our situation. So this is the net force. We have two opposing forces fighting each other, right? And let's say this is positive direction and this is a negative direction. Because last time we did it, and most physics books actually they called it, oh, actually no, I want to do it the other way. This is how most physics books do it, but we can actually throw it upward too. So I want to go the other way, the normal direction. Okay, now let's just conceptually think. Well, let's set it up and then we'll think conceptually. Okay, so this is the golden law of Newton's second law of physics, right? All of the forces put together, vector, is same as mass times acceleration vector. Good? Okay, this itself gives us a differential equation. Now, all the forces acting together here, of course, is this in negative direction. So we have negative energy, just magnitude. So vector is although it's a vector, it's a one-dimensional. So this is positive, this is negative. That's taken care of. And then now you might think, why shouldn't that be positive? right? What you say is pointing up. No, 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 no. It depends on what V, okay? If V is positive, if it's going up, then actually it should be downward. It just means opposite direction of V. You get it? If V is negative, in this case, our V is negative, right? See that? V itself is a negative number going downward, and then that negative sign makes it positive, so it's pointing up, which is our picture at the moment. That makes sense to you? Okay, at this point, before we solve this differential equation, let's think conceptually. Conceptually, what is the situation? I'm going to move this thing out of the way so I can put the picture here. Can we just figure out the terminal velocity from this alone, right? See, terminal velocity meaning this force, it starts small because when you just jumped out of the airplane, there isn't that much air resistance because your velocity is starting with a 0. And then it starts growing as you speed up, right? And once you pick up enough speed, this thing grows, 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 and eventually this length arrow becomes exactly the same length as this. When they match each other, then your acceleration is 0 because your net force becomes 0. You get it? So conceptually, terminal velocity is when this thingy, what am I doing? When this thingy is equal to 0. You know what I'm saying? And let's see what that is. That means negative mg minus kv is equal to 0, isn't it? And like, why shouldn't that be the, no, 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 once again, the direction, right? V is in that direction, this direction, so it's opposite. And then that tells you that V, this is terminal velocity, happens to be negative mg over k. You know what I'm saying? Do you know what I'm saying? Because should be negative number because we are moving downward. You get it? So if we did it the other way, this is positive direction, then it looks actually easier, but I want to worry about this thing going the other way. So I'm going to graph this thingy. So if we have t versus v here, we have terminal velocity like this. This is vt, which is negative mg over k. And then this curve will start here and move asymptotically like this. That makes sense to you? Conceptually, physically, just before we start with the differential equation?
Mr. Kim?
Yeah.
Can you explain the negative thing you were talking about? Like, so is MA supposed to equal to mg plus kv, but since both of them are negative, so...
Okay. This is positive number at the moment because velocity is negative number. We are moving downward, correct? This is a vector.
Yeah.
So that makes this entire quantity positive, correct?
Yeah.
So we have negative and positive, so we add up to 0.
Okay.
Makes sense to you? You kind of get it, but you don't at the moment. It's kind of...
Wait, so what is the original formula? Is it just negative mg minus kv, or?
It depends. If you call this positive direction, then it's just positive mg minus kv. And that's literally
okay. So it's always mg. So it's always minus kv.
Yeah, it's always because it's this is a vector, so it's just that this whole vector is opposite direction of v vector. That's all it's saying.
Okay, and yeah. Okay, thank you.
See,
and it goes opposite as the motion, right?
Yeah. Yeah. Mg is always a positive number, so if I put negative sign, that points it downward. V, k is positive number, but v could be positive or negative depending on the direction of the motion. So this is a positive because v is a negative number. The motion is downward at the moment. Right? Right. Think about it. Okay. Now, so there's that. So that's what we expect. Okay. Now we'll solve this differential equation now. And this with the initial condition v originally is, we call it v naught. So this may or may not be 0. Okay. If it's 0, it makes it so much easier differential equation. But why have it so easy when you can have it nice and complicated? You know what I'm saying? Okay, so let's solve it. Okay, so what we have to understand is this a is a second derivative. This is a derivative of v now, isn't it? Isn't it? So I'm going to divide both sides by m and write this first. So we have a, first let's divide and rearrange it. So we have that is equal to minus kv over m. Let's just put it like that. It's ugly. V and then minus g, right? You with me? And then you're thinking, how the heck do we separate this? This is a separable differential equation? Yes, it is. Okay, dv dt is what a is equal to negative km, and this is what you want to do. You factor this out, so you have just v. This makes the antiderivative so much easier, and this is the trick. Now tell me what's left here. How can you factor something is not there? We at least know this is positive, right? Right. What do you say? Factoring is division, right? Division is multiplying the reciprocal. So this is mg over k, isn't it? Isn't it? Let's check. If you distribute, you get this. If you distribute, m's and k's cancel, you get negative g. Agree now? Now here where I always say differential equation tells you a story. What's the story? Acceleration is depending on this thingy, right? This is always positive, constants. K is constant, m is constant, which means acceleration is always downward at the moment. Yeah, right, sure. And if this is, when this is equal to 0, then your acceleration is 0, correct? This is equal to 0 means that negative mg over k, huh? See, differential equation tells you a story. Okay, it's a description of the physics phenomena. Now, come back to the realm of mathematics, and we separate. So we have dv over v plus mg over k. Good? Is equal to, and then you leave these things here if you know what's good for you, like that. Is how you're gonna separate it. And then you take a derivative, you take an antiderivative on both sides. So it's like integral sign, if you will. So this is ln, and we are sure, right? v plus mg over ka, and is equal to negative k over m t plus c. How are we doing so far? Good. Okay. Now we have to solve this for v. So we take e, or write it into exponential form. So what we have is absolute value of v plus mg over k is equal to e to the negative k over mt plus c. Good. Okay, and we can apply initial condition now, but according to earlier video, there's an easier way. So I'm going to rewrite this. So v plus mg over k is equal to plus or minus, and I'm going to use rule of exponent to write these two separately. I'm going to write this one first, and e to the negative mt. Good, good. Now, this whole thing is a constant, including the sign, correct? So I'm going to replace that with another constant, a, or sometimes b, or sometimes giant c. Let's do a. Okay? So far, so good. And then I'm going to put here where a is plus or minus e to the c. Good. This is the nicest stage to do initial conditions. Okay? So I'm going to do actually two different initial conditions. Okay? So one with red and one with blue. If initial condition is this is nicer one. Let's do this one first, and I'm gonna do more complicated one, okay? If this is the case, in other words, you didn't jump downward, you didn't jump upward, you just jumped out of the airplane with no initial velocity. Okay, when that happens, this v is a function of t, as you can see. This becomes 0, so we have mg over k is equal to a, and then this, if you plug in 0, this becomes 1. So this is it. So what we have is v plus mg over k is equal to a, which is mg over k, and e to the negative k over mt. With me? Y'all with me? Okay, so v is equal to mg over k e to the negative k over mt minus mg over ka. We can common factor that, and that is mg over k, and then e to the negative k over mt minus 1. So far, so good. Okay. This is a little bit harder to see. Let me convert this into this form. Wait, did I forget? No, I didn't forget, right? Yeah, I didn't forget. Okay, let me convert it this way. Now, you're thinking, why the hell would you want to do such a thing, right? Because this is a negative value. Do you see that? Exponential decay function. This is less than 1. So if I put it this way, this is a positive value, so it's easier to see. Right? Let's think transformation. If you have e to the x, right? Actually, I'm going to throw this bunch of transformation. E to the negative x looks like this, right? Well, if you put negative sign in front, it inverts, right? So far, so good. Now we do +1, so this thing elevates now. So what we have at the moment is this, right? Elevate by 1. This minus sign and this whole thing. And then actually this is like whatever. And then we vertically transform this. Oh, actually I screwed up. I screwed up big time. And let me start over, because I didn't realize I inverted. Okay, we have this, right? Let's just think with this. Okay, we have this. So we have this thingy with 1, right? And we lower it. So now we have this. You know what I'm saying? So far so good, that graph. Now we multiply vertical scale by mg over k. So this becomes now mg over k. How about that? Which is exactly the graph that I drew here. You know what I'm saying? Ah, so that's the case. Okay, and I have in Dropbox note, I have the graph of this that I created using graphic program. Okay, now what happens then? Our initial condition is not 0. Let's say we have some kind of initial velocity then at v initial is some v naught, which may or may not be upward or downward. So it could be positive or negative. It could go either way. And then what do you have? Okay, let's check. So this thing now becomes V naught. This is more complicated case. Plus mg over k is equal to a again. Once again, if I put 0 here, this whole thing becomes 1. So far, so good. Now I plug this back in here. So what I have now is V plus mg over k becomes, open parenthesis, V naught plus mg over k times e to the negative k over mt. Good. And then V, finally, as a function of t, is equal to V naught plus mg over k e to the negative k over mt minus mg over k. Good. Okay, so this is a general case. Does this thing really include this case? Yeah, sure. Because if this is equal to 0, then do you see it's the exact same equation as this? Okay, let's check. How do you know that when you got this thing correct or not? Here's how you check. Number one, you want to check this. This value gives us V naught, right? Because that's our initial velocity, that's how we got here. So let's plug it in. If I plug in 0 here, this whole thing becomes 1, right? So we have V naught plus mg over k minus mg over k, they cancel, so we get V naught. So that one checks out. The other one is our terminal velocity better be negative mg over k, right? So the other one that we want to check is limit of t approaching infinity. That's how you find the horizontal asymptote of V. Let's see what that is. This is exponential decaying function, so this dies when you take the limit to infinity. So holding dies, so you have negative mg over k. Exactly what you want. Huh. Amazing, isn't it?